I'm Thorsten Lorenz, work for NodeSource, and yeah, I got bored one day and actually kind of wanted to understand how the computer works, kind of. So, and I thought I would never learn it, and I did, and it didn't take me that long, and this is kind of what this talk is about, to try to get you kind of, is anyone excited about CPUs and assembly and would like to know how it works, kind of, right? Yeah. And like maybe some of you think, there's not enough time, it's probably too hard to learn, maybe, yeah. So this talk is supposed to show you that it's not that hard. And I also built a tool that is supposed to make it a little easier, and I'm going to show that too. So first of all, why should anyone even learn assembly, right? Oops. So, well, it gets you as close to the metal as you can, without actually writing zeros and ones. But it's very close to the CPU, so you can kind of make it bigger. So you can kind of see it, how things work. Thanks. But it doesn't kill you, so that's good. And as I said, since assembly is so close, it maps almost one-on-one to actually what the CPU does. At least if you think about it in a simple way, you can kind of understand what's actually going on inside a CPU, which is important to understand. Even if you work really high on the stack, if you do front-end development or whatever, it's still kind of interesting to know. The other reason why you should learn assembly is because if you want to write really high-performance code, or if you're in embedded devices or whatever, it is important. Like I actually asked, I think Trevor and others, what this actually does. This one makes sure that if this operation is thread safe, without creating a lock on the variable, which improves performance. So in some cases, and this is in Node.js, this is inside libiv. So in some cases, you actually want to drop down to actually handwrite assembly instead of having to C-compile it. But C-compiler actually generates assembly as well, but sometimes it's not doing it the way that you want it. And if you need more performance, you can actually write it. So, and it's important for that. Also, the cool thing is that, as I said, it's so close to the CPU that you can actually assemble your written assembly and outcome opcodes that the CPU can actually process. But then you can use a disassembler and you can get your assembly back without using anything like debug symbols. Like kind of for JavaScript people around here, there's like the kind of like source maps. You don't need any of that. You can go back and forth. It's kind of like as if you had minified code and unminified code, and you could go back and forth without any extra information. So that's kind of cool. So you could take any program and you can look at it. You could look at the assembly. For instance, you could look at the machine code that V8 actually generates from your JavaScript, and you could look at the assembly. But it's too hard, right? Yeah, it's actually not that hard. So I'm going to tell you a little bit about myself. I at some point went to university and actually learned assembly. Took this class, but it had risk assembly. That's what they were teaching. But at the time, I wanted to be a guitarist, so I didn't pay too much attention. I think I got a D+ in the class or something. And then when I got back into programming, I got back through .NET, which is kind of very high on the stack, and kind of removed me very far from what's actually going on inside a computer. And I didn't think that I would ever really learn assembly. And then I became one of the cool kids, and went with Node, which was a little lower level already, but still, you don't really see what's going on. And then I had to look into C. This is not a trumpet. This is the letter C. And the I. So I had to look into C. And as most Germans will know, C and A kind of go together. So once I had C, I could also learn assembly. So C I started to look into again, like maybe 2 years ago. Assembly, I got me this book. That was less than a year ago. And I started looking into it and just went through some examples and kind of did them. And then I needed a project, so of course I wrote a Pong game. It's like the thing to do, but I got kind of halfway done with the Pong game, and then I realized if I do more of this Pong game, it's not going to really teach me anything. I kind of learned what I could learn from it. And also, the world doesn't need another Pong game. So I decided to think of something that I could do that doesn't only help me, but also helps others. And I kind of looked into CPU emulators, which is really interesting. Basically things that emulate a CPU in software. like in the browser. Has anyone seen Linux running in the browser? Yeah, but again, no one needs another one of those, right? So I figured, why not do one that actually helps people learn assembly, like that are in the same position that I was in. It's pretty boring by now. You want the demo, right? Okay, we're gonna get to the demo, but first we need to do a little CPU crash course. So CPU, on a very high level, has a control unit, and the control unit looks at the instruction register, which tells the CPU where the next instruction is, which is just basically like a hexadecimal, just a number, but it means something. And then a control unit knows what it means, and then it tells the ALU, which is the arithmetic logic unit, what to do. And then you can think of like signals go in and signals go out, and then something changed, and that's basically how a CPU kind of works. Here's an example. So we're adding 1 to ECX. ECX in this case is the destination register, so it serves as an input, but as well as an output. So we're taking whatever is in ECX. Let's say there was 2 in there. We add 1 to it, which is 3, and then we store 3 into ECX. So that's kind of how you can think of, like, you have these inputs coming in, outputs goes there. And that's pretty much all there is to it. Of course, there's more smartness going on. In real CPU, they do a bunch of things, like they fetch a bunch of instructions beforehand, so they don't have to hit the memory all the time. There's caching, there's pipelining, there's branch prediction. That's all not something you need to know about, and I don't even know about it that much. And definitely my emulator doesn't know about it either. So now comes the real demo. So here's the thing that I built. It's called Visulator because it visualizes and it emulates. So on the left side here, we're seeing basically, well, let's show this on the bottom first. This is all the information that Visulator got. These are opcodes. It's just basically codes for the CPU, and the CPU knows what to do with this. And then just for illustration purposes, or to have it look nicer, on the left side we show the actual assembly. So you still see the opcodes on the left here, and the assembly to the right. And I'm actually using Capstone. Has anyone played with Capstone before? Capstone is this cool thing that kind of disassembles code, and it also works in the browser because you can script it. So this is all done in the browser, by the way. All it gave it was these opcodes on the very bottom. And on the right side, we see registers, and we see them twice. So here we have all the registers, EAX, EBX, and ECX, and so on. And then we show them in binary format, and we show them in hexadecimal format. So they're twice. And the other thing to notice is they can be addressed in different ways. You can address the entire register, or you can take the lower 2 bytes, and that would be, for instance, AX instead of EAX. And then you can divide those even further, and you can address the lowest byte as AL in case of EAX, and AH for the higher one. So, and now what we can do here, so we can step through this, and you can see how things are changing, right? So in this case, I'm moving 0x7FFFF into EAX, and you can see how it changes over there, right? So it's kind of like, assembly is actually really not that hard if you just go instruction by instruction. And here you can see what's actually happening. And on the bottom, you can see how binary addition works. So, by the way, all these visualizations are all just CSS. So I'm very proud I figured that out. So no JavaScript animation at all. All the transitions in CSS. So, and then here, this is a very interesting part. We see flags. And that's basically how you can make any decisions in the CPU. For instance, here we have a 0 flag. And if you click on any of these things, it will give you information. So it's kind of meant to be like a learning resource, and it's still kind of in its infancy. It will grow hopefully more. But basically, you can get information about what's going on. So I wanted to show an example here. So here, for instance, I'm going to move 2 into BL. So BL is this part over here, right? So when I go to the next one, we see that now BL became 2. Can everyone see that, by the way? Is that too small? Okay. And now I'm going to decrement 1. And now watch the 0 flag over there. Okay? So if I decrement by 1, BL became 1, right? So the 0 flag doesn't light up. Okay? When I decrement again, now it became 0. That means the result of the last operation was 0, 0 flag lights up, and now we can do conditional jumps. We can say jump if the last operation returns 0, and that's basically how I can do loops and all these things. And I'll show probably a loop later. Yes, and here another thing is interesting is the EIP, that's the instruction pointer. It's currently pointing at 111, that's because we are at address 111 over here. Yes? And another one is ESP, that's the stack pointer. And you can see that it's pointing at FFFF. That's because the stack grows actually from the top to the bottom in memory, and the other memory grows from bottom to top, and then somewhere there's some safety zones so they don't meet in the middle. But now if I push a variable onto the stack, you will see the stack pointer change. See that? So now the stack pointer just moved one down because we have a variable now there, and if I want to pop off the stack, it would just go right there and pop off the variable. Right? So that's pretty much, and all the things have also links here, so you can click on this, and yeah, you can get all the information you want. That's kind of supposed to be like, if you want to learn assembly, this is supposed to help you. And the ideas came basically from debugging, right? If you're starting out with assembly, you should most definitely use something like this, and while it's not fully featured, at least a debugger, and step through your code and look at what's actually going on. Like, what does each instruction do? Oh, this register changed and this flag lit up and so on. And I'm going to have some resources where there's some cool there's a cool plugin that you can use with GB that helps you visualize that. Yes, and the reason why it's not fully featured is because this is the entire opcode table. I was had the bad idea to implement x86. So yeah, so it's very, very long. And my opcode table is about this long so far, and it was already a lot of work. But it's already helpful to at least a learning tool. This is also something you would have to look at if you wouldn't use a debugger, and it's not easy to just figure that out by itself. So I'm going to show another thing that I actually wrote to help me build Visulator. So what would you say if I told you, this is probably too small, right? What would you say if I told you I have over 27,000 tests to make sure that my CPU actually works correctly? You probably think I'm crazy, right? Or like maybe bored, or like have too much time. Well, but I do have this many tests. So here they're running, and they make sure that my CPU actually works exactly like it's supposed to work. But no, I didn't write all these tests. What I did is I figured I have a CPU right here, and I know that CPU works. Right? So what if I just run the opcodes through my CPU, and then I look what that outputs, right? And I look at like what are each step, what are the register values, what are the flag values, and then I somehow save that somewhere, and then I pipe the same opcodes into my CPU, and then I compare and make sure that it's the same. And that's pretty much what's going on here. This is all this logging stuff. But here you can basically say I'm just comparing each register with other registers and so on. And what I wrote for this is it's called GUI. It stands for GDB Assembly Inspector, or Informant, or something. Basically what it does is just takes GDB, tells GDB to step through it, prints out the results. But you can also use it if you're developing it. So, for instance, I can take a binary file. So if you see it at the bottom, maybe I put it to the top. So this is basically a program that I wrote in assembly, and maybe I'll just open it over here. So basically I just wrote this program. So every time I needed to test something, I just wrote assembly. So here we can see it does a bunch of stuff, and basically it's supposed to test that I have the jump if equal and jump if not equal instructions correct, right? And then basically here and then I compile it, and then I can actually just debug the compiled one, and it prints me this information out. So, and on the right, we can actually see the comments. They're just all generated, so these comments just indicate to me what flags changed and what registers changed, and so on. So, so I don't have to only look at this, right? Because it would have been way harder for me to implement this if I only have seen that. And then there's huge PDF files you can download from, I think, Intel. That is just, yeah. So you definitely need this. All right, so I have some resources here that you can use. So the first book that I showed is actually the book that I showed for learning assembly, actually the second book. It's a really good one, I think. You should definitely familiarize yourself with the GDB debugger. Unfortunately, you can't really use LDB for assembly. It's just a pain. It doesn't really work on Linux, and on Mac you can, whatever. Just use GDB. There's a cool plugin for GDB. It's called PETA. It's kind of a reverse engineering tool, but you can use it for good as well. So that's really good. Assembly informant I already told you about. Capstone I told you about. One more thing I'll show is while I was learning assembly, I wanted it to be like Node, obviously. So I created packages, kind of, so you can install, if you need a certain assembly function, you can install it. And the installer is called curl. So you just curl like a specific file, and then you get this assembly. It's also probably good for learning because it's very isolated pieces of code that do certain things. And you can probably learn from it, and you should probably also add to this. So I try to make this like a package repository. So that's kind of interesting. And then I made the Visulator documentation. I tried to make this also kind of a resource. Where did it go now? Here. So I tried to document everything I learned about while I was building this and kind of what it's doing and so on. So this could also become kind of a resource for you to learn about assembly and stuff. Right, and then of course, if you want to learn more about like where Visulator is going, I'm going to keep trying to develop it further. You should follow me on Twitter, Thorsten Lorenz, and I'll let you go lunch.